So complex numbers come up over and over and over again in the field of acoustics and in noise control and in vibrations. And sometimes people have trouble doing the kind of conceptualizing what complex numbers mean and why they're so useful. So I wanted to go through a couple examples to try to give you a better intuitive feel for what's happening, not so you can not just understand the algebra and the mathematics and sort of the operations that we're doing, but also get a better idea of what intuitively is going on when we manipulate complex numbers. So I'm going to start off with a complex number. I'm going to call it Z1 because I'm going to have some other complex numbers as we go. And that's 4 minus 3i. So, that's algebraically. Let's draw that. We're going to draw it as a vector. And here I've got the horizontal is the real part of the complex number, and the vertical is the imaginary part. So I'm going to draw it as a vector that starts at the origin and goes 1, 2, 3, 4 in the positive real direction, and then 1, 2, 3 in the negative imaginary direction. I'm going to draw that as a vector like that. So just some terminology. The real part of our vector Z1 is 4. The imaginary part of the vector of the complex number is -3. And I'm going to keep jumping back and forth between the terms complex number and vector because I'm jumping back and forth between an algebraic and geometric conceptualization. The magnitude is I take the real part and square it, and then add the imaginary part and square it, and then take the square root, which if you work that out, you would get 5. That's the length of this vector. So this is a 3, 4, 5 right triangle. So the magnitude of the complex number is the length of this vector. So if we wanted to do another manipulation, like add a second complex number, let's say we have Z2, second complex number, that is -2 plus 4i. Algebraically, adding these two, so say Z1 plus Z2, all I do is add the real parts together. So 4 minus 2 is 2. -3 plus 4 is 1, so 2 plus I. That's what algebraically it means to add two complex numbers together. But geometrically, if I wanted to do this in terms of just this picture, what I do is I draw Z2, but I draw it with the end of it being at the origin of it being at the end of this vector. So it's sort of we call it a tip to tail. So I'm going to start it there and go -2 in the real direction, and then +4 in the imaginary direction. So I'm going to draw it like that. And then the sum is just I connect the origin to the end of the blue arrow. So on this picture, this is Z1, this is Z2, and then the purple one is Z1 plus Z2. And just convince yourself that this is equivalent, right? So 2 plus I, that's what I got for the purple vector, the sum. I moved over 2, 1, 2, and then up 1, I, for the imaginary. So that part is pretty straightforward. conceptualizing adding numbers, adding complex numbers, both algebraically and geometrically. So let's actually move on to what is slightly more complicated, and that is multiplying. So I'm going to just write this again. The same example vector 4 minus 3i, and draw it the same way. So let's talk about multiplication. If I can multiply by constants, so let's say 2 times z1, and I just multiply real and imaginary parts, I get 8 minus 6i. What that corresponds to in the graph is stretching this vector. So if I went all the way to 8 and minus 6 and drew that from the beginning, you would see that, yeah, it just stretches that vector that way. Or I could do something like multiply by negative 0.5, and I would get negative 2 plus 1.5i. And then over here, something less than 1 corresponds to shrinking instead of stretching, and negative sign just means it's going to point in the other direction. So it would be a vector like that. So that part's pretty straightforward, multiplying by a real constant. What if I wanted to multiply by I? So I take my z1 vector, I'm going to multiply it by I. Algebraically, I take 4, so I get 4 times I, and then negative 3i times I. The two i's multiply together to give you a negative 1, so I get a plus 3 here, which I'm going to keep using the convention of putting the imaginary part on the right, so I'll do 3 plus 4i. I should have written that in another color, so let's 3 plus 4i. So let's graph that. So 3 plus 4i looks like this. And what you might notice is that that's the same as this original vector here. It's just rotated by 90 degrees. And you might convince yourself that that's always going to happen, because what I'm doing is taking what was the real part and making it the imaginary part, and then taking what was the imaginary part and making it the real part, but sticking in a negative sign. So that is equivalent, corresponds to rotating by 90 degrees. And if I multiplied by another I times I times I again, I get, well, these two i's give you negative 1, so I get a negative z1. So that would be pointing the other way. Let's just draw that on here. What is it? Negative 4 plus 3. So that would be that. That would be another 90 degrees. So if this was z1, this is z1 times I. This is z1 times I. If I multiplied by another I would get the same thing rotated by yet another 90 degrees. And if I multiply by I a fourth time, I get the original back. So multiplying by I corresponds to rotation by 90 degrees. And I could do something like, let's say, z1 times 2i. Well, that corresponds to do the rotation and then do the stretching, or the other way around. So that's the same as if I took this long vector here and then rotated that by 90 degrees, which I would get up to all the way up to there, I suppose. So this would be z1 times 2i. So we have, so far we've talked about addition, adding two vectors together. You kind of stick them tip to tail. We've talked about multiplying by a real constant. And we've talked about multiplying by an imaginary constant. If we wanted to multiply by something a little more complicated, that's also not too difficult. So let's say I've got my same vector, 4 minus 3i, and we'll still draw that on here. There's z1. If I wanted to multiply that by z2, and let's say z2 is 1.5 plus a half I. And I'm not going to add those together, I'm going to multiply those together. So I want to say z1 times z2. And now you've got a couple options here algebraically, but what I'm going to do is multiply all of z1 times the 1.5. So I'm going to say 1.5 times this 4 minus 3i, and then multiply all of z1 times the 1.5i. And I can kind of do that multiplication. I get 6 minus 4.5i, and I get, let's see, positive 1.5i, oh sorry, positive 1.5 plus 2i. And then finally, adding all that together is 7.5 minus 2.5i. So, again, algebraically, very straightforward. Just kind of multiply all the different combinations here, and you'll get to the right answer eventually, as long as you keep track of when you're multiplying i's together and you pick up a negative sign and whatnot. But let's figure out what that means geometrically over here. So what we're going to do is take z1 and multiply it by the real part of z2, and that corresponds to this stretching. And actually we get this value here. So let's just draw that stretched. So 6 minus 4.5i, that is that. So that's, let's call that 1.5 z1. And then we'll do this part where we multiply by the half I, which is actually this, 1.5 plus 2i. And if you remember, multiplying by half times I corresponds to make it half as long and rotate it by 90 degrees. So half as long and rotated by 90 degrees. Let's see, that puts us 1.5, and so right about there. So this vector is 0.5i times z1. And then I can add what I've drawn here as the blue one and the orange one together. And in order to add those, I need to kind of shift the blue one down here. Again, kind of a tip to tail addition. And let's see if we can get this right here. I think we'll end up with something like that. And then the sum is that. So this is actually a right angle here. Important to note. So here's the sum, which is z1 times z2. So what we did was we broke this up into a real part and imaginary part that we're multiplying by. The real part corresponds to just stretching in the same direction. The imaginary part corresponds to stretch it and then rotate it 90 degrees, or rotate it and then stretch it. But then you just add up the answers. So you sort of treat this as two different operations. Now, what would happen if we wanted to multiply by a different amount? So say we had some vector, and I'll draw the same vector just for fun, but say we wanted to rotate it by an amount theta instead of, so it's going to stay the same length, but we want to rotate it by an amount like this, theta. How would we express the amount that we need, the complex number we need to multiply the red vector by to get to the blue vector? Well, what we're going to do is use some geometry, and hopefully we won't mess this up too much here. But we're going to break this up into a part that's along the direction of the red vector, and a part that's perpendicular at 90 degrees. So I'm going to put a line like this. So I think if we think about this right, there's a part that is that leg of this triangle and a part that's that leg of this triangle. So the blue vector, which is what we're trying to rotate the red one to, is the sum of this part that's along the direction of the red vector and this part that's at 90 degrees. So if I wanted to keep the magnitude the same, so just rotation, not stretching, I take the red vector, I multiply it by a, let's see, cosine theta in that direction, and multiply it by a sine theta in that direction. So the blue vector, let's say that's z2, that's equal to z1, the original vector, and I have a cosine theta in the direction of the red vector, and I have a sine theta in the perpendicular, and the way I express rotation by 90 degrees is just to put an I there. So now we're maybe seeing the point of Euler's formula here, because this thing in purple, which corresponds to rotation by theta, let's just write that. And theta has to be, theta is going to be in radians here. According to Euler's formula, e to the I theta is this same thing, cosine theta plus I sine theta. So when I write this z2, the rotated version, that's just z1 times e to the I theta. So it's just a compact way of writing rotation in this a rotation by theta in this this complex plane here. So what the thing that comes up over and over and over again in acoustics and vibrations is what would happen if you made theta a function of time. So let's say theta, the angle I'm going to rotate it by, if theta is equal to omega times t, where omega is the angular frequency and t is time. What that is the angle that it's rotated by. You have some base vector z1. The angle that it's rotated by, theta, is increasing with time. So at some angular frequency omega. And omega might be something like, it's in radians per second. So if it goes one revolution per second, then it's omega is 1 radian per, or 2 pi radians per second. So let me show you what that looks like, kind of animation wise. So we have this vector here that's swinging around, and it always has the same magnitude, right? It's got, if I can sort of trace the circle that it's following, like that. It's swinging around. It's increasing theta in time. So this, when we write in acoustics something like z e to the I omega t, this is what we mean. That's really important. So there's some vector that's the baseline that and then this is so this is the complex amplitude, and this is the rotation in time, or we can say the time harmonic component. And it just goes around. Now, I want you to notice some things here, and that's that, like, it doesn't actually matter where this vector started. It started wherever it started at time is equal to 0. But in general, unless we have another vector to compare it to, this is just swinging around. We don't really care where it was at time 0. So what we can do is, instead of just watching this as a function of time here, we can plot the real and imaginary parts as a function of time. So if we plotted the imaginary part as a function of time, I wrote in the wrong place here, but this is the imaginary part of, let's say, of z e to the I omega t. And this is time. So you might notice this is just a sine wave or a cosine wave. And where that comes from, it can come from just this cosine theta and sine theta we were looking at before. But if you wanted a more conceptual way of looking at that, just kind of follow the top of the arrow here, the head of the arrow, as it goes around. And if I can plot I'll plot the real and the imaginary parts at the same time here. So the imaginary part, the end of this just follows the arrow as it goes around and around. That's the imaginary part. So I'm just plotting the vertical component of that. And then the real part, I'm just plotting the horizontal component of that. So this is the real part of z e to the I omega t. And now time is going this way. So this is a really important thing to keep kind of in the back of your mind as you're manipulating all of these complex numbers. That when you see e to the I omega t, what you should think of is there's this vector in the complex plane that's rotating around counterclockwise at a given frequency. And if omega was twice that, it would be going twice as fast. And maybe we'll see some examples of that in a future video. But so the important things to keep in mind is amplitude's not changing. There's no amplitude change contained within this e to the I omega t term. The sine and cosine part just come from the projection of this rotating vector onto either the imaginary numbers or the real numbers. So I hope that gives you at least a little bit of a conceptual idea of what's going on when we show these kind of complex numbers everywhere. It's good to have both an algebraic and a geometric understanding of that. So thank you, and we'll see you next time.